Hi, and welcome to the Specim IQ tutorial series. I'm Gail from Specim, and in this tutorial I will present the identification model creator and go through the different steps involved in it. A model is a non-editable executable which is exported from a model project. This can then be used in an application to define how the data is processed.
Before starting the model creation, let's look at the relationship between applications, models, and projects. A model contains information about data processing, information extraction, classification, visualization definitions, and settings. All of these properties are defined in the model projects. Once the model project is completed, it is compiled as a model. You can choose a single model to be used in an application project. The application defines how the data recorded with the Specim IQ is visualized and saved. The application combines the model settings with the imaging settings. Again, these modifications are done within an application project. Once the application project is completed, it is saved as an application. An application can then be installed to the Specim IQ camera. Remember that a model project needs to be saved as a model before it can be used in application projects, and an application project needs to be saved as an application before it can be installed to the Specim IQ camera. Now, let's return back to the Specim IQ Studio software and begin model creation. To start building a model, go to the Application's main view and open the Models tab. If you have already built and saved some models, they appear on the left on the My Models list. If you have model projects, they can be seen on the right on the My Model Projects list. We will start building a new model by creating a model project. Select Create New from the Burger menu next to the My Model Project list. In the Project tab, enter the basic model information: model project name and the author. Give your model project a good description. After you have built your model, you can come back here and include some details about the used wavelength range, the binning values, whether preprocessing is on or not, and the number of classes. You can use the model version number to track changes you might make to your model project. You may also add an author logo to brand or label your model. Then click the Create Project on the top right corner. The new project prompt opens where you can change the project folder name and its location. Please notice that you must first fill in the required fields marked with an asterisk on the Project Information tab before you can proceed to the other tabs. Once the project is created, the buttons on the top row change from Create Project to Save Project As and Save Project. With the Save Project As button, you can save a copy of the current project with a new name. The Save Project button will save changes to the current project. It is advised to save your project every now and then to prevent losing information, for example in case of an unexpected power failure. Now we are ready to move on to the next tab. In the Data tab, you select one or more datasets as the training data you wish to use for your model, and from this create areas of interest, also known as AOIs. You must open at least one dataset and create at least one area of interest. Select Open from the Dataset Burger menu. Select the datasets you wish to use. And press Open. The selected datasets are shown in the dataset list. Create a new AOI by selecting Create New from the AOI's burger menu, or by double-clicking the visualization area. To create a new area of interest, click and hold the left mouse button on the image and then drag to create the AOI. Currently, you can only create square-shaped AOIs. It is advisable to create a reasonably large AOI so that you can better adjust the class settings later on. You can rename your AOIs from the burger menu on the right. In this view, you can also examine the data by clicking on the image to see the pixel spectrum. You can click several pixels to view their spectra side by side. The spectra of the pixels you choose here will be visible in the next tab of the workflow, the Wavelength tab. Click Clear Spectra to remove the spectra from the graph area. You can also change the image's RGB band values either by typing the value into the text box or by dragging the colored lines in the graph area. If you wish to return back to the default RGB values, click Reset. Once you've finished creating your AOIs, you can then move on to the next tab. In the Wavelength tab, you can get an overview of the spectra in the different areas of interest and define the wavelength range from which the data will be collected. You can activate a maximum of 5 AOIs at a time by clicking them on the list of the AOIs on the left. The color box next to an AOI will indicate the color with which the spectra will be visualized on the graphs. First, let's select just one AOI to explain the functionality. The first graph shows 30 randomly chosen spectra from each activated area of interest. If you have chosen additional spectra directly from the AOI, they are also shown in the graph. The second graph below shows the variance as a function of wavelength, taken from the spectra from the activated area of interest. As a rule of thumb, the higher the variance is, the more spectral changes can be observed from the data. More spectral changes can lead to a better identification of materials. In this view, you can also select a binning for the spectral data. Binning means averaging the values of the consecutive spectral bands into a single value. Binning values of 0, 2, and 3 are available. Binning will lower the spectral resolution by the binning value chosen, but it will also help to decrease the amount of data. From the third graph, you can see the effect of the binning to the group of spectra from the activated area of interest. Again, below it you can see how the variance detected from the AOI changes after binning. To limit the wavelength range used in the calculation, either double-click one of the graphs or select Edit from the burger menu. Here, you can select to use either the full wavelength range, limit it, or make separate range selections. Adjust the beginning and ending of the spectral range by clicking and dragging the green vertical line or the orange marker on top of the graph. You can also type the desired wavelength range directly into the text box. If you want more than one wavelength range, click on the plus symbol above the graph. You can make a maximum of 4 separate ranges. The minimum width of the range is about 30 nanometers, and the minimum distance between the ranges is also approximately 30 nanometers. To delete a wavelength range, simply click the cross symbol. If you are using binning, it will limit the precision with which you are able to make the wavelength range selections. Once you are happy with your wavelength range selection, press Save. If you click Close after you've made any changes, all of the changes will be discarded. On the top right corner, you can see the Include the Workflow option. By default, this setting is on. However, if you choose to switch it off, the model will function using the whole wavelength range without any binning. Now we are ready to move on to the next tab. This is the Classes view, which is the most important step in creating models. In this view, you define the identification classes. Select an area of interest and open the class creator by either selecting Create New from the Classes Burger menu or by double-clicking the image. The workflow in this view contains 3 steps. First, click on the image to find a suitable reference spectrum. Click different areas of your target to find the most suitable spectrum. When the selection is done, press the Add as Reference button and name the reference. The reference is added to the reference spectral list. Second, activate the class mask. Once the mask is calculated, define the correct threshold value with the slider. Moving the slider to the left will loosen the masking criteria, allowing more pixels to be selected in the class. Moving the slider to the right will tighten the criteria, making the selected spectra to match the reference spectrum more precisely. We use the Spectral Angle Mapper algorithm to assist your selection of the threshold value. The reference spectrum is used to find the relative distance of each spectra on the image. The values we are getting from the SAM calculation are placed in the background of the slider and visualized as a heat mask. The yellow areas refer to groups of spectra that have the same difference in the selected reference spectra. This information will help you to detect the different groups on the data and adjust the threshold value so that only the correct areas are selected to the class. The third step, after you are satisfied with your threshold value, is to name your class in the Class Info text field. And you can also choose a color for the class if you are not satisfied with the default color. A good practice is to select the color so that it is distinguishable from the target in the RGB image. Press Create when you are done. The class is now successfully created. You can then create several classes by repeating these steps on the same area of interest or different areas of interest. You can adjust the class settings in the Classes tab by selecting one or more classes from the list and then pressing Compute. Once the results have been calculated, you can move the threshold slider in the main view. You also have the option of only visualizing one class at a time. If you wish, you can also test your classes with the other areas of interest. Select any area of interest that you want, class or classes, and then press Compute. You also have the option of merging classes together. This helps to enhance the identification classes, especially if you need to work with tight threshold values. To merge classes, select the classes you wish to merge by holding the Control button on your keyboard and selecting the desired classes. After the selection is made, select Merge from the class's burger menu. You can now choose a name and a class mask color for your new Merge class. You can also add classes to a Merge class afterwards by selecting the Merge class and selecting Edit from the Classes menu. Let's first create another class to be merged with our new Merge class. You can also add classes to a Merge class afterwards by selecting the Merge class and selecting Edit from the Classes burger menu. Select the class you wish to include in the Merge class and press Apply. You can also remove classes from the Merge class in this window by deselecting the classes you wish to remove. After you have created the desired number of classes, you can move forward to the Preprocessing tab. If you need or want to use the Preprocessing option, you can include this to the workflow by choosing the option from the top right corner. In order to use this feature, you must have a single continuous wavelength range. So, if you have created separate wavelength ranges, Preprocessing won't be available. On the Preprocessing, you have the possibility to smooth possibly noisy spectra with the Savitsky-Golay filter. You can choose only the polynomial order that will affect the smoothing. After selecting the desired order, select the classes you want to test and press Compute. On the graphs below, you can see the selected classes, their unprocessed spectra, and the smooth spectra. It is good to check the effect of the smoothing by showing both spectra in the same graph by selecting the Display Raw Series checkbox. Double-click the graph to enlarge it. After you're satisfied with the results, you can save the project and move forward to the next tab. In the Classification tab, you can select the visualization method for the SAM algorithm. Heat mask visualizes the mask in various shades. The shading is selected from the threshold value set for the class. The pure color that you have selected for your class is given for the threshold value 1, meaning a full match between the recorded and reference spectra. The lightest color set for the class refers to the set's threshold. This means that the lighter the mask color is set for the pixel, the measured spectra are further from the reference, but they still belong to the created class. The binary mask visualizes the mask with one solid color. Select your desired visualization method, the classes you wish to test, the area of interest you want to test it with, and press Compute. The results are then visualized below. In the results view, you can toggle the background RGB image on and off. Once you are happy with the classification visualization method, move on to the next tab. The Test Run tab is the final step of the model creator and is the place to test the model with full datasets. Ideally, you should have datasets of the target from several illumination setups and backgrounds. This makes the model testing ideal, since the application itself might be used in various environments with various setups. Again, datasets are selected for model testing from the Datasets menu. You can see the dataset info on the right. Double-clicking the visualization image allows you to research the data. Enlarge the graph by double-clicking it. You can select one or several datasets and then press Compute to test your model. The results are then calculated and visualized. If you're happy with how the model is functioning, save the project and then save the model. Fill in the information as required. The model is now saved. You can see the ready-made model on the My Models list. This model is now ready to be used in an application project.
In this video, we went through the workflow of creating an identification model on the Specim IQ Studio. If you found this video useful, do give it a like, and please subscribe to the Specim Spectral YouTube channel to follow our tutorial series on the Specim IQ. Thank you for watching, and see you in the next video!